Scientists have calculated that it takes 320 attoseconds for an electron to jump from one atom to another during a typical interaction. Roughly speaking, 1 attosecond is to 1 second as 1 second is to the time since the Big Bang. But that's not the shortest interval ever recorded. The shortest interval of time ever experimentally measured is the time it takes light to cross a hydrogen atom, an estimated 247 zeptoseconds. This is 1,000 times briefer than an attosecond, and it's still not even close to a Planck second, the time scale at which any theoretical measurement breaks down completely. The reason for this breakdown is complicated and has to do with the other Planck units that the Planck second is based upon. A Planck second is the time it would take light to travel a Planck length. A Planck length is the distance light would travel in a Planck second. That definition might seem circular, but it doesn't really matter. The Planck length does not have any precise physical significance. It is a common misconception that it is the pixel size or smallest possible length of the universe, when really it is a standardization of physical units based on certain observable quantities like the gravitational constant and the speed of light. What matters is that it's a hard theoretical limit to our physical investigations. The shorter the wavelength of a photon, the smaller the object that photon can interact with. If it can't interact, then you can't detect it, and we don't have recourse to any smaller forms of energy that we could detect or measure. The Planck length is so short that we could never create a photon with a short enough wavelength to interact with it, and thus we can never measure anything smaller than it. With these inherent limits of our scientific investigations, we can only speculate what happens on the most brief and minuscule scales of the quantum world. As we reach these unimaginably brief and tiny interactions, the imagination is naturally drawn towards Zeno's paradox of Achilles and the tortoise. For a runner to overtake their opponent in a race, it requires them to traverse an infinite series of diminishing distances. Half the distance, then a quarter, then an eighth, and so on, such that any movement implies an infinite regression, an infinitely complex interaction with time and distance. In the quantum realm, this paradox takes on a new dimension. Here, time and space blur into a haze of probabilities and uncertainties, where particles can exist in multiple states simultaneously. This is a realm where our classical understanding of physics breaks down, and new strange rules govern the behavior of the universe. The same problem becomes all the more apparent in the quantum world. For the sake of argument, let's suppose that there exists a fundamental form of energy exchange or physical change, which is the briefest, most basic interaction possible. If there is such a thing as a simplest possible state change, then we would have to ask an important question. Is this interaction completely instantaneous, requiring zero time, or is it unimaginably brief, requiring an interval of time so small we can't conceive of it? On closer examination, either case is self-defeating. If there is no interval elapsed in this briefest interaction, then there is no change and no progression of time. This fundamental interaction would be useless as a unit of time because zero time elapses. It's nonsensical to say that something changes without time elapsing, since physical change is the entire basis of our conception of time. But if we consider the second option, an interval so brief that it defies our understanding, we face a different puzzle. In this scenario, the smallest measurable unit of time is not zero, but infinitesimally close to it. This opens up a whole new realm of possibilities where the very concept of time is a series of almost imperceptible steps, a staircase leading into the unknown depths of the quantum world. In this mysterious domain, the paradox of change becomes a doorway to understanding the fabric of reality itself. Here, each fleeting moment is a testament to the complexity of the universe, a reminder that even the simplest interactions are imbued with profound significance. Time is an undetectable thing, gauged only by the relative movement of things we consider to be consistent, like the movement of the sun or oscillations of cesium atoms in an atomic clock, but we cannot escape the relativity and uncertainty of these arbitrary references. The Heisenberg principle tells us we cannot know a particle's position and momentum simultaneously. Consequently, we have no firm evidence of time ever elapsing for a particle. We might catch a glimpse of a particle, like a single frame in a video, but in the next frame, which appears after an indefinite amount of time, or zero time in this example, the particle is already elsewhere. In the nonsensical world of timeless subatomic changes, There are no gradual processes, merely an infinite number of instantaneous jumps everywhere at once, like a world made of changing pixels on a video screen, except with an indefinite frame rate, 1 frame for every 0 seconds, or 10.4393023 frames for every 0 seconds. It makes no difference because we're dividing by 0 and the frames have no duration, and yet somehow these durationless events would have to form the basis of the passage of time. Option 1 is very clearly untenable, but option 2 is no better. If there is some interval of elapsed time in our shortest possible physical interaction, we run into the opposite version of the same problem. What defines the passage of time in this interval, which is shorter than our shortest unit of time and which has no physical referent? The existence of some interval of time necessitates some other mechanism or referent for the passage of time, which is somehow more fundamental than our sub-quantum leap, which is supposed to be a one-step process. As simple as it gets. Some might say that the lack of a physical referent means that time does not locally exist or change in this interval, but this is circular reasoning. The entire notion of an interval implies that time does to some extent exist, and that it is still passing as we wait for the particle to pop back into existence. If time isn't passing or doesn't exist, we can't have any length or quantity of it. We are left with a paradox whereby the smallest unit of time is inherently undefinable. To have any conceivable duration, it must be defined by a smaller unit of time. But if it is defined by a smaller unit, then it is not itself the smallest unit of time. In this labyrinth of paradoxes, we are reminded of the illusion of continuity. The seamless flow of time as we perceive it is a construct, a grand illusion woven by the fabric of our consciousness. Just as a movie is an assembly of countless still images, our perception of time is stitched together from countless fleeting, imperceptible moments. These infinitesimal intervals, though elusive and enigmatic, form the very essence of our reality. The grand illusion of continuity challenges us to look deeper, to question the very nature of existence, and to embrace the complexities that lie beneath the surface of our everyday experiences. In the end, the true nature of time remains one of the most profound mysteries of the cosmos. It is a puzzle that beckons us to explore, to question and to wonder, and perhaps in the pursuit of understanding we may find not just answers but a deeper appreciation for the intricate dance of particles and moments that shape our universe.